Okay, this is an A to D converter, and this is the foundation of the A to D converter. So you can design one with these components, and this will allow you to understand how an A to D converter works, like the ADC 800 families and other types. So in this converter, we have different elements. We have a constant current source, a voltage follower, a non-inverting voltage comparator, a flip-flop, and a logic oscillator without delay, without startup delay, and one half monostable or edge detector, and finally a binary counter. So the purpose of this converter is to convert the input voltage V in into a binary reading, into a binary equivalent. So the circuit starts here. Even though we don't have a power up or reset, so I'm gonna start assuming that Q is 0 and not Q is equal to 1. So if not Q is equal to 1, this transistor is in saturation and it is grounding this capacitor, and it is sending this capacitor to ground. So the capacitor is right here on 0 volts. We know there is a collector emitter voltage here, 0.1, but for this purpose we will consider 0 volts. So and because Q is 1, Q is 0, so you have a 0. This is not Q also. You have a 1. If you have a 1, so you have 5 volts here and 5 volts on the other side of a capacitor. That means the capacitor doesn't have a bias. 5 minus 5 is 0, so it is like an open circuit. So the resistor R2 works as a pull-up resistor and keeps the input in logic 1 and the output is logic 0. Okay. So the reset is in 0. So of course we didn't apply a power up reset, which we can do later in another version of this circuit. And when we have to start this circuit to operate, we have to press the Q output. We have to press it to. We have to press the push button to start. So with this one, we make a set equal to 1, and an input on the set will generate an output Q equal to 1. And therefore, this enables the gated oscillator and starts sending frequency to the counter. And also what happens, because Q is 1, not Q is equal to 0, so the transistor goes from saturation to cutoff. So it is open, and because it is open, the current was initially flowing, the constant current was initially flowing through here. Now the current will flow through the capacitor. And because it is a constant current, the capacitor will start charging as a ramp until it reaches the same voltage we have here. So let's say we have 1 volt, or 1 volt here. So the voltage follower will give me here 1 volt as a voltage reference. And that'll create a reference for the comparator. When the voltage reaches the same voltage than the reference, so when the capacitor reaches 1 volt right here, the comparator will send a pulse resetting the flip-flop, and it'll make it 0. At that point, when by the way, what happened when this one was 0? When this output was in logic high, this was in logic 0. So when we received the ground, so at the beginning of this pulse, we had this type of pulse created by the capacitor, and we generated a reset. That means that during the time t, in the first fraction of time right here, reset pulse was applied. That way the counter started with zeros. When the pulse ends, when the T pulse ends, which is proportional to this time, the gate goes to zero, so the oscillator stops oscillating, stops sending frequency, and the frequency will stay there. And the circuit is waiting for a new pulse to arrive to start a new conversion. So when this one ends, the conversion is ready and the number will be there. Another way to see this A to D converter is what happens if we apply a higher voltage. So if we apply, let's say 3 volts. So 3 volts will be our reference. And when the capacitor reaches 3 volts, you see when we pulse this, it goes open, the capacitor C starts charging, and when it reaches the same voltage that we are applying, 3 volts, we will generate a longer pulse, and the ramp will create a longer pulse here, so more pulses will be applied to the binary counter, and that will create a binary reading which is proportional to the voltage we are applying. So if we are applying 3 volts and you are expecting and you want to calibrate it to number 300 in binary code, so you have to adjust this frequency by putting here a logic, a trim pot right here. So you adjust it, and to avoid having 0 ohms in the trim pot, we will place a series resistor. This one can be 5K, it's a standard value, 5K, and a trim pot. So it can be a 100K, 200K trim pot. So you adjust it to the frequency that you need to adjust this number, and so that this number is directly proportional to the input voltage. And the current that we are getting here is VDD, which is the voltage applied to the transistor, minus VBE, base emitter voltage, minus base voltage, divided by RE. Okay, so we know the constant current or collector current, and the time it'll take for this ramp to charge, it'll be RC. So R is equal to V over I. In this case is the constant current, the collector current, and times C. And we have to multiply this equation by the percentage of this or the ratio that 3 has over the total voltage. In this case, 3 over 5. So 3 volts over 5 volts. And we know the collector current, so you just substitute it and you will get the final equation. You substitute this IC by this IC. Okay, so this is a foundation of analog to digital converter, where the capacitor gets charged by a constant current source. Okay, thank you.